So our two main types of pumps are centrifugal or positive displacement pumps. So our centrifugal pump, we'll have a look at a bit of a clip later, but essentially it consists of an impeller, then we've got a casing, which are normally cast iron, and these are in the shape of a volute or similar to a snail cam. So as the diameter increases with rotation. So basically liquid is flung into this volute casing, and this ultimately increases velocity and pressure on the discharge. Suction is always through the center of the impeller. Okay, any pump we've got essentially two different types of sealing arrangements, just as we do with our our stern tube. Well, we got three with our potential with our stern tube, but two with our pump. We've got gland packing here, gland packing to seal our shaft, stop any liquid pass, or we can have a mechanical seal, which has two faces under spring pressure, and we have a carbon graphite faces. Providing the alignment is set up on these, we get very good life and no leakage and no adjustment out of a mechanical seal. All right, so that was centrifugal. Positive displacement pumps, they trap a fixed amount of fluid, and then they force or displace that fixed amount of fluid into the discharge. So this is one type. This is a piston pump, common on larger bilge pumps, really. Haven't seen them in sort of any other application really on vessels, but so our piston moves up and down, and these are a double acting piston. So basically, as the piston is moving down, it's creating a low pressure area above the piston, and so this allows the suction seat to come off its seat and for this volume to fill with liquid. And then on the discharge, as it's moving down, it'll displace that fluid, open the discharge valve and discharge. And then as the piston moves up, it creates a low pressure on the suction side, so the suction valve here would open and fill that space, and then the liquid that's on top of the piston will be displaced and will come out through the discharge valve and out the discharge pipe. Any positive displacement pump needs to have a relief valve. If a valve is closed on the discharge side of a positive displacement pump, then the pump will actually continue to build pressure until something is destroyed. So we need to have a relief valve. As opposed to our centrifugal pump, where if we have a discharge valve closed on here, if we close it while it's running, we'll get water hammer. But what it will tend to do is just cavitate the water in here, which won't be great for the pump, but it won't continue to build up pressure. It's just going to add friction in the water and create cavitation and heat up the liquid that's in there. We've got the potential to run a centrifugal pump dry, whereas most positive displacement pumps, the piston pump wouldn't be too bad, but a lot of them we cannot run dry. We'll have a look at different types. Okay, with the centrifugal pump too, we can start these with the discharge valve closed, and this can be a help to try and build up suction pressure. A centrifugal pump, these are potentially the most common pump we have. They're low volume and high displacement, so very good at pumping low pressure through here. Generally, we only use about 1 to 2 bar on a centrifugal pump. We can probably push it up to about 7 or 8 bar, but as opposed to a positive displacement pump, we can get a hydraulic pump to deliver 250 bar. So they're a low pressure pump, but we can deliver large volumes of water. We just increase the size of the pump to get more volume. Okay, a positive displacement pump, as I said, we need to have a relief valve on any of them. We've talked a bit about gear pumps with hydraulics.
Centrifugal pumps are the most preferred pumping devices in the hydraulic world. In this video, we will have a conceptual overview of working of centrifugal pumps. At the heart of the system lies the impeller. It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluid surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, at discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues. This is the reason why priming is important for centrifugal pumps. If no water is present initially, the negative pressure developed by rotating air at eye of impeller will be negligibly small to suck fresh stream of water. Impeller is fitted inside a casing, so the water moving out will be collected inside it and will move in the same direction of rotation of impeller to the discharge nozzle. Here you can note one specialty of casing. It has got increasing area along the flow direction. Such increasing area will help in accommodating newly added water stream and will also help in reducing exit flow velocity. Reduction in flow velocity will result in increase in static pressure, which is required to overcome resistance of pumping system. Here you can see more details of vanes inside impeller. They are backward curved vanes with state-of-the-art eye configuration. This vane is extracted from a Kirloskar pump model. If pressure at suction side of impeller goes below vapor pressure of water, a dangerous phenomenon could happen. Water will start to boil, forming vapor bubbles and spoil impeller materials over time. This phenomenon is known as cavitation. More the suction head, lesser should be the pressure at suction side to lift water. This fact puts a limit to maximum suction head a pump can have. Careful pump selection is required to avoid problem of cavitation. Current impeller type is enclosed. Semi-open and open impellers are also in use depending upon application. If the working fluid is cloggy in nature, it is preferred to use open kind of impeller, but they are slightly less efficient. Mechanical design of centrifugal pump is always challenging. A shaft is used to connect between the impeller and motor. Since water pressure inside casing is huge, a proper sealing arrangement is imperative in arresting water leakage through shaft casing clearance. Mechanical seal or stuffing box-based mechanism is used for this purpose. Impeller is mounted on bearings, but at suction side of impeller, it is not advisable to fit a bearing since it will block the flow. So bearings have to be fitted at the other end. This means impeller is mounted like a cantilever. For high flow rate pumps, a bearing housing with cooling oil is necessary for improving life of bearings. We thank Kirloskar Brothers for their technical support and creation of this video.
Our diaphragm pump, fairly straightforward. Reciprocating shaft onto a diaphragm. As the diaphragm moves up, creates low pressure, opens the suction valve, and then as the diaphragm moves down, closes the suction valve and opens the discharge valve, displaces the fluid in there. Vane pump, they're commonly used in hydraulics and pneumatics. Basically, often we've got springs in here, but not always. Acting centrifugally, these will follow the outline of the casing, and we just have a suction through here, and it creates a low pressure as the vane moves out, displaces that fluid out through the discharge port. Flexible impeller, you would be well familiar with these, our rubber impeller. Obviously, because they're rubber, they won't run dry. We'll have a look at a bit of a clip.
We've got these big rubber impellers. This is one of our bigger pumps, and they actually go all the way down to this itty bitty little thing, about that size. All of these flexible impeller pumps have something in common. They need a cam. Some cams are in the shape of sleeves, some are replaceable or removable, and others are actually molded into the pump body. The gist of it is the cam kind of rolls or folds over the vanes and makes a kind of like a larger and smaller cavity, if you can
Hey, Mike, why don't we go to the lab and actually show them how an impeller pump works? Let's get out of here.
Let's go. So this is a pretty cool display Jeff and I made. We've got ourselves a commercial duty water pumping, and I took the end cover off. Now you shouldn't run impeller pumps dry, but we put a little bit of lubricant just to make sure it doesn't damage the impeller. It's hooked up to a 500 amp variable power supply, which means we can drop the volts down to about 2.5 volts and still have this spin. Give you an idea what's going on. So that cam is squeezing those vanes. What that does is once the vanes come on this side, it creates a negative pressure, which draws the fluid up into the impeller cavity, down and around, and again, that cam squeezing those vanes, folding them over, pushing the fluid out the discharge. What we're going to do is we're going to put a clear end cover on and give you a better idea what's going on inside the impeller pump. All right, here we go. We've got the clear end cover on. We've got the seal, the O-ring seal around it. We've got some dishwashing liquid here. I'm going to turn the power on. Watch this. That impeller spinning, creating that vacuum. Here comes the material. Swings down, and there it goes. Pumping right through the system. That's pretty cool, huh? It's coming in, going down and around, being squeezed out that side. See if I can slow it down a little bit. How's that? There again. It's coming in, down and around. That cam squeezing those veins over, pushing the fluid right out. Now check this out. This is the pump running at 2.5 volts. Let me turn it up to 12 volts. That's 12 volts. That pump is running full force. Well, Jeff, that was pretty cool. We used that clear end cover, showed you what's going on inside that pump, the little cavities, how they form, they get bigger and smaller, and how they push the fluid out. I hope that helped out. What do you think?
Yeah, that wraps it up, Mike. Thanks for watching this episode of JAPSCOtech.com. I'm Jeff Lander.
And I'm Mike Irving.
Come back soon. We'll have some more videos for you.
As we know, a bilge is the lowest place on a vessel where liquid can accumulate, and some of the requirements that we need for our bilge system are that we've got to have 2 bilge pumps. All right, if it's up to 20 meters vessel length, then we need 2 pumps, but one of them can be a hand pump. And for a vessel greater than 20 meters, then they need to be power operated, and it needs to be 2 different power sources. So it can be engine driven and electric driven, etc. We need to have suction strainers on the suction pipes for our bilge wells. So our strainers, sometimes called strum boxes, a way of making sure rags and different crap don't get sucked up through the bilge system and to the pump. Our bilge pumps need to be self-priming, so it shouldn't require any manual priming to get the pump working. And all of our suction valves have to be non-return valves for our suctions and for our overboard discharge valve. All right, this is to prevent backflooding. So we'll talk a bit more about backflooding. We also need bilge alarms to notify us if bilge levels get high. And it is advantageous to have a bilge holding tank, a place for us to pump our bilges, TK tank. And the reason is, what's the most predominant liquid we have in our bilge? That's a question for you. Well, the answer is seawater. Predominantly, we're going to get leaks, and majority of our liquid is going to be seawater. And so often vessels will corrode from the outside in. We spend put a lot of energy, in dry docking on coating and protecting with anodes to prevent corrosion on the outside of the hull. But what about on the inside of the hull? So, if we can keep our bilges dry, that's the main aim. And if we've got a bilge holding tank, then we've got the potential to pump any bilges daily or, throughout our watch and basically reduce that corrosion that can occur. All right, we've talked a bit about oily water separators that we might have on our vessels. And so coming back to back flooding. So back flooding is basically an occurrence where water can get from one compartment to the other, and it can go through from one bilge to another. If we didn't have non-return valves on our bilge suctions, it could come in from an overboard discharge valve back to our compartment into our bilge. It can be through a hose trailing over the side. If we stop suction, then it can siphon back through. So any methods to which we can get one compartment flooding another is back flooding. Let's have a look at the schematic of this bilge system. We'll be tracing out a bilge system on the Bluefin when we come and do the pracs for our bilge, and so we'll trace it by hand and then sketch up a schematic drawing. But it's going to be a little bit more complicated than this. This is fairly simple. So we've got a number of watertight compartments we got here, 4 peak, 2 holds, that's 3, 4 for the engine room, 5 for the steering flat. So 5 compartments, but we've got 6 bilge suctions. Yep. So 1, 2, 3, 4, 5, 6. So this is our bilge suction strainer or strum box. That's the schematic symbol for it. It's got like a perforated plate showing some sort of filter. And this here is our bilge suction manifold. So it's one pipe that has all valves on it. With our schematic drawings, it doesn't have to show the exact route of and the location of the pipe work or where the valves necessarily are. It can be drawn to be simplistic, but we should know that if we trace a pipe from here, we should be able to end up somewhere at this end in the steering flat. Whether or not it curves around and goes through there is irrelevant. We always keep straight lines on our schematic views as well. And so this manifold, it's shown as almost the length of the vessel. In reality, it's going to be very short. The idea of our manifold is that we can go to one section to find where we need to pump in an emergency situation, open the right valve, start the pump, and to be able to reduce the effects of flooding. So that's our bilge suction manifold with all of our suctions, and we've got 2 pumps. We've got a bilge deck wash pump here and a standby bilge pump. In reality, normally what we have on a larger size vessel is a bilge pump and normally a fire and general service pump. Now, a general service pump or GS pump means that it can be used for different services, general services. So can be used as a bilge pump or as a fire pump, and often it can be used as an auxiliary seawater cooling pump for our main engine and perhaps some other things. So, but this one has 2 pumps, bilge deck wash and standby bilge pump. So from here we can suck from the manifold with either pumps, and this one allows us to also pump seawater, which we can use for priming. It needs to be self-priming anyway, but with this one we've got the ability to use a deck wash hose, and on most vessels that would go to various fire hydrants on the deck and possibly in the accommodation or around the accommodation. Okay, so we know a schematic symbol for a pump, a unidirectional pump, pumps in one direction, and with this one we can pump overboard in an emergency. That's a good question. Can we pump our bilges directly overboard even if it's an engine room oily bilge? Well, the answer is no. We've got to have 0 oil discharge. But in an emergency, are we allowed to pump overboard even if it's oil? Well, the answer is yes. If we are risking foundering the vessel, and potentially we're going to sink, and to save the loss of property and potentially life, then yes, we are allowed to discharge in that sort of emergency situation. And this one also allows us, we said, to deck wash, or we can pump to a bilge holding tank as well. Whereas this pump here will only allow us to go directly overboard with our bilge. Alright, as I said, we'll get much more familiar with our schematic drawings when we come to sketch ours up of the blue. Let's take a look at our bilge system. So we've got two pumps for our bilge system. We've got our main bilge pump, and we'll look at that one in a moment. I wanted to look first at our alternative pump, which is this guy here. It's a bilge ballast GS pump, or general service pump. So it performs three functions really. We can use it to pump our bilge, we can use it to pump our ballasts, or we can use it to run the seawater cooling for our main engine if our main engine's seawater pump fails for any reason. So the reason it's general service pump is because it performs different services. So it's a centrifugal pump, so our suction is always through the centre, and here we've got two suction valves for our pump. One is called the direct bilge suction, and it's a red safety coloured painted valve. The reason for this is we're going to look at our bilge main in a second, and if we came to an emergency situation where we're flooding the engine room, it would take us a while to set up to find out which valves we need to open. So there's one valve on most larger vessels that's called the direct bilge suction. If we open that valve and we got our overboard discharge valve, all we need to open is we just start the pump and it'll pump our engine room bilges straight away. Now it doesn't go through the bilge manifold, it sucks directly from the bottom of the hull. So it's just a pipe that goes straight down, there's no suction strainer on it, it's just we open that valve, discharge valve, start the pump, and we're pumping straight overboard. So then we have our suction for our sea suction, and that's this valve here. So if we're going to use this pump for two reasons, we're going to use it to pump seawater into our ballast system, or we want to use seawater to pump to our main engine for emergency seawater cooling. So we would use that valve, and then we've got a suction here on this side for our bilge. So if we open this valve here, then we can suck our bilges, and if we open this valve, this one's for our ballast system, so we can suck out from our ballast tanks. So, okay, let's look a bit more closely at the bilge system. So if we open this bilge suction valve, and if we wanted to pump directly overboard for an emergency situation, we would have to also open our discharge valve, which is this one. Now that would be that would send our bilge water to this large pipe just behind me. We would have to open our overboard discharge to send our bilge water overboard, and then there's one other valve that we're going to need to open, and that's for our bilge suction manifold. So our bilge suction manifold is this row of valves here. So these are all of our bilges on the entire vessel. So we've got one in the sonar trunk, in the tunnel, one in the thruster space, we've got one forward engine room, one in the bosun's store, one in aft accommodation, forward accommodation. So any of these valves, if we've set it up like that, we open one of those valves, start the pump, and that will pump overboard. Our ballast system, we saw the ballast valve down there, the ballast suction. If we open that up, we've got our seawater suction open, then we can deliver through our ballast system through this same valve, and if we open that up, there's two more valves. There's one down aft for our aft peak tank. I won't show you where that is, but it's a line straight off this pipe work. And there's one for our fore-peak tank. So to discharge our ballast water to our fore-peak tank, we would open this valve. So that's connected straight off that pipe. So we would have seawater pumping to our fore-peak. Similarly for the aft peak, only the valve is down aft. We would have to set up the same valves there, open the aft peak valve, and we can pump seawater into our aft peak tank. We also have our main bilge pump. So we looked at our bilge ballast general service pump. This one's dedicated as a bilge and ballast pump. So it's also a centrifugal, so it takes its suction from the centre, and here we have our suction manifold. So what this gives us the option of pumping from is from our C-suction, straight off our C-suction main. We've got another bilge direct, so that's going to suck straight from the engine room bilge. Then we've got our ballast suction, so we can suck from either of the two ballast tanks, aft peak or fore peak tank. And then we've got our bilge suction valve. So if we use the bilge suction valve, then we've got to go to the bilge suction manifold to pump the right bilge out of the space. And then this one on the discharge side of the pump, it comes up to a branch line. We've got an overboard discharge, which in this right now is padlock closed, or we can send it up to a sludge tank, which is up on the Monkey Island, which is above the bridge, or we've got the ballast fill line. So if we open seawater suction and the ballast fill, then one of the aft peak or fore peak tank valves, then we can pump our ballast tank. The difference between our ballast system and our bilge system, our bilge suction valves are always non-return. The same with our bilge direct valve. It's got to be a screw down non-return valve. Our ballast system operates differently because we use the same valve to fill and to discharge. There are no non-return valves on it. So our fore-peak tank valve works as the suction point and the fill point for that tank. So it's not a non-return valve, it's just a screw lift valve, and what it relies upon is that we always shut the valves after we use it. So whenever it's the same with a bilge system, we close all the valves at the finish of operation. It's critical with our ballast system because there are no non-return valves to act as a check and balance in the system. It relies on our integrity, our due diligence as an engineer to close and isolate the system afterwards. Our bilge system, by contrast, yes, we need to pay just as much diligence to it, but we do have non-return valves in the system. What that is there for is to prevent back flooding. So if we get flooding in one compartment, we can't get that flooding act through the pipework and flood another compartment. It'll only flow in one direction. So hence the non-return valve. Our ballast system, as opposed to our bilge system, on our manifold we do not have non-return valves, and that is because the same valve is used to fill or to suck from our ballast tank. So how do we prevent potential for back flooding? Well, the only way we can on our ballast system is to ensure that we keep all these valves closed, which we do on a bilge system anyway, but we've got to be extra diligent with a ballast system. So, all right, so this one, so we've got potentially 6 tanks that we can fill with seawater. Why do we ballast? Well, generally it's to provide stability, and on cargo vessels we use ballast systems when we're in light ship or zero cargo. To keep the vessel stable, we'll fill our ballast tanks with seawater just to provide that stability. So we've got fore-peak tank, number 1 port and starboard, number 2 port and starboard, and an aft peak tank. Okay, now generally our these tanks would either be double bottoms or a wing tank, and so we've got 2 pumps capable of ballasting for us. And if we're going to fill, then this is a schematic symbol for a seawater suction. You know, if you think of the you know, the shape of a hull and a deck. Anyway, that's might help you remember it. But anyway, that's a suction through to our ballast pump, and we can discharge. This is a little bit wrong, this drawing. If we imagine this pipe work's not here, and the discharge is going to come straight back to our manifold, and then if we open one of these ballast valves, then we can fill this up with seawater. And conversely, if we need to strip a tank or pump it out, then we would open whichever relevant suction valve, say to number 1 starboard, and from there then we can open the suction valve on one of these pumps and then discharge straight overboard. So as I said, no non-return valves on the manifold, and we've got to ensure diligence in order to close the valves after any ballast operations. This is showing one type of our domestic freshwater system. So obviously we've got a freshwater tank or tanks, and we're going to use a domestic freshwater pump to our domestic services. Now this system uses a new press, so particularly for larger systems, because this is going to be split up into, you know, potentially different decks and a lot of different services, what we want is that the moment someone turns their tap on or flushes the toilet, then instantly we've got water pressure already there, and this new press system allows us to do that. It's a pneumatic pressure vessel basically, and the way it works is we've got a cylinder with a diaphragm, and there's air pressure on top. This is supplying an amount of pressure to keep a certain amount of pressure in our system already charged. Okay, and we can apply air here if the pressure is low, and to keep that pressure regulated. All right, from here we've got motor starter control circuit, and essentially when the demand is active from the domestic system, then instantly, because of the air pressure in the pneumatic system, the pneumopress, then our water will start to flow under pressure. Now as soon as that gets down to a certain pressure, then it will start the domestic freshwater pump, and this pump will be supplying the pressure. As soon as the taps are all turned off, then this pump will keep pumping until we get a certain amount of pressure in the pneumatic system, and then it'll turn off. But what it's done is applied a certain amount of pressure charge to the whole domestic freshwater system. So the moment someone turns the tap on again, there's instantly pressure there. We can also make freshwater on board vessels. This is one type of system that uses evaporative effect of seawater, so and they call this an evaporator. This one uses jacket water. This whole thing is under a vacuum from a vacuum pump, so we can boil seawater which comes in through here. So we apply seawater, and it boils basically at our jacket water temperature, around 80 degrees Celsius, perhaps even less, and then we get this mist, our steam, and then we have seawater cooling passing through here, and this mist then is, through that cooling, forms condensate or condensed water, and then gets pumped off to a tank. We can also, more commonly on smaller vessels, we have a reverse osmosis system, which is a semi-permeable membrane, which will, if we pump it at high pressure, will prevent any salts from our seawater passing through this membrane, and we end up with fresh water.
This membrane carries a charge, and also the pores are very small, letting the tiny water molecules pass through,
That tickles.
but rejecting molecules of, well, just about everything else. The flow of water molecules through the reverse osmosis membrane is facilitated by keeping the pressure higher on the outside than the pressure inside. This process, called reverse osmosis, is how the water is able to pass through the membrane while leaving the other stuff behind. The pressure outside pushes, enabling the tiny water molecules to squeeze through the pores towards the low pressure inside.